So now let's go into our final notebook. And here we're going to finally do some machine learning. So we'll start by loading in that data that we prepared in the last two notebooks. You can see that we're working with the same variables and it's been split up into a training and a test set. So now we're going to fit a machine learning model. So there's this workflow of you fit a model, you predict using the model, and then you evaluate how well it does. So what are each of these three steps? So fitting is where we take the data and we pass it into our model. Then the model is going to go through the data using whatever algorithm it's based on, and it's going to look for patterns that relate these x variables into the y variables. So our algorithm is going to try to figure out, based on these values here, how does that show that the patient is negative for diabetes, or positive, etc. So we're not going to go into this in too much detail, but there are other resources like data camp classes or Medium articles where you can learn more about this. But there are a bunch of different machine learning algorithms, and we're going to use one called random forest. So we can import this from our library called scikit-learn, and this is the machine learning library that we're going to mainly be working with. And you can import random forest classifier. And we're going to create a model by saying CLF, which stands for classifier, equals random forest classifier. And this is our object that we're going to be working with. So next what we're going to do is we're going to fit the model by calling .fit, and then we pass in the data we want it to learn from. So x_train and y_train. And what this does is it has gone through the data and tried to look for patterns to be able to predict whether or not the patient has diabetes. So, is that it? Are we done? Well, we're not sure yet. So now we need to know how well our model does. So we had earlier split up our data set into a training set and a testing set. And so now we're going to see how well our model does on patients that it hasn't seen before. So we're going to create a variable called pred by calling clf.predict, and then we pass in the data that we want it to predict with. And so xtest, this is data that the algorithm has never seen before. And if we look at what this looks like, you can see that they're all zeros and ones, which is what the labels look like also. So let's compare the truth and the predictions. So this is the first 25 labels, so actually whether or not the patient had diabetes. And this is the predicted outcomes. So you can see that often these are the same. So for example, the first one are both 0, meaning that the patient did not have diabetes, and the algorithm, the model, predicted that they did not. But in this one it's different. So here, 1 is the actual value, the truth, but 0 is predicted. So what does that mean? Well, that means that our model failed to recognize here that the patient has diabetes. So this is called a false negative, because our model said that it was negative, but it is not. And the reverse problem is over here, where the patient actually does not have diabetes, but we predicted that they do. And that's called a false positive. So we want to know how well our model is doing. So one way that we can do this is we're going to calculate a few metric scores. And these are values which tell us how well our model is doing. So we're going to use this function called accuracy score to give us the accuracy. So we get an accuracy of 0.7. So that means that out of 70% of these predictions, or out of all these predictions, 70% of them are correct. So is that a good performance? Is that good enough? We don't know. That's kind of a tough question. So for starters, what we're going to see is we're going to see if any other models do better. So like I'd said earlier, there are a lot of different types of algorithms. Each one works a little differently and might work better for a certain data set. So the best way to know what your best model is going to be is just by trying each of them. So we're going to import all of these different machine learning models, and we're going to evaluate each of them on our data. So we'll save each of them in this dictionary called models. And then we're going to loop through each of these. We're going to fit each model to our data. Do the same thing. We're going to fit, predict, evaluate. So let's create a helper function here to do this for us. So let's call this, let's take a function and you need to give it a name. So let's call it train model. And it's going to take two arguments. Class CLF, which is the classifier, and then the name of the model so that we can see which model it is. So the first thing we're going to do is we're going to fit the model to our data. Then we're going to predict it with our test data. Then we're going to calculate. We're going to take the y test, which is the truth, and the prediction, which is pred, and we're going to calculate the accuracy, print it out, and return it. Okay, so now let's loop through each of these. You can see that each of them have different performances. So let's visualize this. So here's some code which is going to sort how well each of our models did based on the accuracy, and then visualize so that we can compare. So this might look different for you because there's a little bit of randomization here. But for me, the best one was this naive Bayes model. So if I go up here, I can see that NB is Gaussian NB, which is Gaussian naive Bayes. Random forest did second best, and my worst model was a decision tree. So again, we're not going to go into the details of each of these models, but what we are going to do is we're going to take this highest performing model and do a little more analysis with it. So earlier we looked at these examples of where sometimes the model said that the patient was negative for diabetes, but they were actually positive. Sometimes they said that the patient was positive, but they're actually negative. And so we call these false positives and false negatives. So something to consider is, which is worse, a false positive or a false negative? So I think the answer there is that it depends on your task. So let's see. To think of an example, let's say that you are you're doing a screening for breast cancer, for example. So like in the Digital Doctor, this is an app which assists radiologists in looking at images. And the goal of the system is to tell you that there might be something wrong. So a false positive there would mean that the algorithm says that there's maybe cancer, there's breast cancer, and there isn't. And a false negative would miss that there's cancer when there actually is. So I think in that example, you really want to find all of the patients who have breast cancer. If we fail to identify a case of breast cancer, then that means that that patient might not get the treatment that they need. If they have a false positive, then maybe that could be bad. Maybe it could result in some treatment that they didn't need or having to do more procedures. But one could make the argument that a false positive is better than a false negative there. But let's say that you have an algorithm which is going to make the decision all on its own, which of course would never really happen, but imagine that it does. Makes the decision that your leg should be amputated. In that case, I'd probably not want it to be a false positive, because that means my leg would be amputated when it didn't need to be. So it really just depends on the situation, but we need to understand how many false positives and how many false negatives we're dealing with. So we're going to look beyond accuracy, and we're going to look at these three metrics: precision, recall, and F1. And so here's what each of these metrics tells us. So precision tells us that if our patient has diabetes, how likely is it that our classifier is correct? So, oh, excuse me. Okay, I misstated. These get confusing. So precision says that if our classifier says a patient has diabetes, so if our prediction is positive, how likely is it that they are actually positive? So a system which has a lot of false positives is going to have low precision, because of all the times that they say that a patient has diabetes, it's not very many times that they actually do. So kind of the flip side of this is recall. So if a patient actually has diabetes and our classifier predicts with it, how likely is it that the classifier will predict that they have diabetes? So a system which has many false negatives is going to have low recall because there are lots of patients out there with diabetes that it's missing. And then F1 is the balanced average of these two. So often the F1 is what we ultimately want to get to be the highest. So let's look at the model that did the best. So for me, it was the Gaussian NB. So I'm just going to copy this. And now I'm going to fit it to the model, fit it to the data, and then predict. And now we're going to do this thing called the classification report. And we're going to look at, for patients with diabetes, we're going to say labels equals 1. What are our metrics? So you can see that our precision is 0.77, our recall is 0.52, and our F1 is 0.62. So take a second to look at this and look at whatever metrics you got. And does this look as good as it did before when we just looked at accuracy? It's not really. So, my accuracy for the naive Bayes was like 0.72. Now the F1 is only 0.62. So the reason for that is that these metrics give you a more detailed perspective of what is wrong with the model. So does our model get more false positives or more false negatives? Well, our false positives are quite high. Our precision is quite high. So we have a precision of 0.77, but our recall is very low. And if you can remember, precision measures how many false positives you have, recall measures how many false negatives. So we have a low recall, which means we have a lot of false negatives in our system, which means that there are lots of patients with diabetes that our system is not finding. And so, is this good or bad? Well, that depends on your users, on your use case, and you'd really have to take that to whoever you're working with to understand if that's good enough. But there are some things that you can do to make it better. So we're not going to go through this, but there are plenty of other resources if you want to go through these steps. But basically what you do is you just kind of mix things up. So like in this XKCD comic, which is where you just pour a bunch of data in. If the answers aren't right, just keep stirring and keep trying again. And that's kind of how machine learning works. So you'll try different things and eventually you'll get the highest performing model. Okay, so this is kind of a lot of information to take in, but I hope that this was a useful introduction to machine learning with you. So if you want to continue learning about machine learning, here are a few resources. DataCamp has a lot of classes about doing machine learning with Python or with R. There's a great textbook here. Coursera is a free online resource. So there's lots of resources to learn more. And if you have specific questions about this notebook, let me know and I'd be happy to walk through any.